Okay. This is where you should be in the note packet. The standard for this one, I can solve exponential and log equations. That's the first foremost thing that you're going to have to be able to do. And then I can solve a log equation where I need to use the properties of logs first to condense an expression. Alright, there are two types of exponential and log functions that you'll need to be able to solve. One type is where one-to-one properties are in place. And the other type is when you have a normal exponential or log equation where one-to-one properties are not in place. So how do you know which one to use? One-to-one properties must have exponential or logarithmic terms on either side of the equal sign. And we'll see examples of that in example 1. Meaning, on both sides of the equal sign, you're going to have like an exponential set equal to an exponential. So you're going to have two exponents, one on either side, that have an x in the exponent. Logarithms, you're going to have a log term on both sides of the equal sign. Normal exponential or log equations have either an exponential term or a log term on the same side of the equal sign. So, I should say, or one exponential term or one log term on the same side of the equal sign. Okay. So one-to-one properties. I should write if. The first one we're going to write down is for exponential terms. So if b to the x equals b to the y, if that's a true statement, then x must equal y. Example, if 2 cubed equals 2 to the x, because the bases are the same, in order for those expressions to be true, then x has to equal 3 in order for 2 cubed to equal 2 cubed. Same thing if you have log. If log b of x equals log b of y, then it also has to be true that x must equal y. For example, if you have log base 2 of x equals log base 2 of 5, then it has to be true in order for that to be an equal relationship or a true statement, because you're saying that this is equal to this, then the arguments must be the same. So x must equal 5 in order for that to work. Okay, and then example 1, we're going to make an a and a b. Okay. And let's start with 3 to the 2x minus 3 equals 9 to the 5x. Now, because you have exponential term on either side of the equal sign, we know that because both exponents have an x in them, so they're both functions of x. And my base, two different numbers, we know we have to use one of these one-to-one properties. But in this case, it doesn't fit the property quite yet because this is saying if b to the x equals b to the y, meaning this is the same value. The bases are the same. In this case, they're not the same, but we can make them the same. Because when we can rewrite one of these numbers to look like the other one without losing its value, which you will have to be able to do. So we're going to rewrite 9 as 3 squared. 3 squared is still 9, so I'm not changing the value, I'm just going to change the way that it looks so that it fits this property. Now here you have a power and a power. When you have a power and a power, you can simplify by multiplying them together. And now it fits the property, if b to the x equals b to the y, then x equals y. So now that my bases are the same, I can take the exponents and I can say, well, in order for that to be true, then my exponents have to be equal to each other. And then I'm going to solve for the x that would make them equal. So I'm going to subtract 2x and divide by 8. So, in this case, if x equals negative 3/8, then both sides would end up being the same value if you were to punch out on a calculator. Okay, let's do another one like that. 2 to the 3x plus 1 equals 8 to the 6x minus 4. All right, again, because I have an exponent or an exponential term on either side of the equal sign, I'm going to use the one-to-one properties. But in order to do that, I have to make sure my bases are the same. So I'm going to rewrite 8 as 2 cubed. Again, not changing the value of it, but just changing the way that it looks. And I get that expression. Now, the reason I get 18x minus 12 is because we have a power and a power like we have there. You multiply them together, so I need to distribute it through. Now that my bases are the same, in order for that to be a true equation, my exponents would also have to be equal to each other. So I'm going to set them equal to each other and solve to find the x that would indeed make them the same value. So I'm going to add 12, subtract 3, divide by 15. So if my x is 13 over 15, I would get the same value on either side. Okay, go ahead and flip it. And then we're going to work on solving the regular exponentials and logs. First step to solving exponential and log functions is you're going to isolate the exponential or logarithmic term. Meaning, get it by itself on one side of the equal sign. Then, your second step, if you have a log function, you're going to raise each side to be a power. This is called exponentiating each side. Okay. Basically, and you'll see it played out in an example here shortly, but you raise each side to be a power, or make each side a power. If you have an exponential function, if that's what you're dealing with instead, then you're going to take the log of both sides. Now, in step 2, you need to make sure that you are using bases that match. So if you have a log function and the base is 2, that when you raise each side to be a power, that your base for your exponential term is a 2. Your third step, solve for x. Because what's going to happen in step 2 is you're going to be able to cancel out stuff, because keep in mind that log and exponentials are opposites of each other, so they do cancel each other out. All right, for example 2, make an a and a b. Got the time here. Okay. First thing that we're going to, or this is just solving exponential equations. So 3 times 2 to the 4x minus 1 plus 10 equals 15. Alright, now notice we don't have, this looks very different than the ones we had on the previous page where we had just one term on each side and they were both exponential terms. In this case, I only see one exponential term, this one right here, because it's the only base that's raised to a power that has a function of x. So I'm going to get that by itself. The first thing I'm going to do is subtract 10 from both sides. And then divide by 3, because the 3 and then that exponential term are being multiplied. So you get 2 to the 4x minus 1 equals 5/3. Alright, now in order to get rid of your exponential term, you have to use the opposite function. So So this is the exponential version. The opposite function would be a log. And because the base is 2 here, I'm going to take the log base 2 of both sides. When you do that, they cancel out, giving you 4x minus 1 equals log base 2 of 5/3. Again, keep in mind the reason they cancel each other out is because they're opposite functions. So when you take the log base 2 of an exponential term that has a base 2, they cancel each other out and you're just left with the exponent. You can also think of it as, if you use the properties of logs, that would come out to the front. Log base 2 of 2, if you were to punch it in a calculator, is 1. So then you would still be left with the same thing. 4x minus 1 equals log base 2 of 5/3. Okay, now to solve for x, I'm going to add 1 to both sides and divide by 4. Now, when you punch it out in a calculator, keep in mind that this log base 2 of 5/3, to punch it out in a calculator, you have to use the change of base formula. So, I'm going to punch that out first on here. ln of 5/3 divided by ln of 2. That part. I'm going to add 1 to that, and then divide by 4. And I get x equals 0.434. Okay. Example 2, we're going to do a very similar one. Let's go 5 minus 6 times 3 to the 5x equals 12. Okay. Again, I only see one exponential term. This is the exponential term that I see because you have a base raised to a power that's a function of x. So I'm going to isolate that by first subtracting 5 from both sides. Then dividing by -6. And then at this point, we're going to take the log of both sides because you want to do the opposite function to get rid of the exponential term. So I'm going to take the log base 3 of both sides. Over here, it cancels out your exponential term, leaving you with 5x. And you have that expression. Then we're going to divide by 5. And then again, to punch it in your calculator, we're going to have to use the change of base formula. So ln of -7/6. Oh, that's an issue. So sometimes you're going to come across a step here. And when you go to punch it out, you get a no solution. The reason you get a no solution here is because with logs, you can't have a negative argument there. And if we were to graph this, this is a graph that flips over the x-axis. So if it flips over the x-axis, it's going to look something like that. And if 12 is what we want it to equal, 12 is way up here. There's no way that that graph is ever going to cross 12. So that's why you end up getting a no solution there. It's because you wouldn't have a place where they actually cross. Okay. Let me check the time. Okay, for example 3, make an a and a b. We're going to solve a couple logarithm functions here. Okay. Now again, if there's not a logarithm on either side, then this is one that you would solve using your steps instead of the one-to-one functions. I see one log term here that I need to isolate and get by itself. So I'm going to add 8 to both sides. Divide everything by 4. 18 divided by 4, oops, reduces to 9 over 2. We'll keep it as a fraction. And then in order to cancel out the log, because now we're at the point where we need to use a function to get rid of the log so I can get to my argument, we're going to exponentiate both sides, meaning both of the sides of my equation are going to now become exponents. And the base of the exponential term is going to have to be the same as the base for the log. So pretend this is now an exponent. This is now an exponent. We've exponentiated both sides. Those cancel because they're opposite functions. So we're left with 4x plus 4 equals 3 to the 9 halves. And then we're going to solve for x. So 4, divide everything by 4. So x is going to equal 3 to the 9 halves minus 4 all over 4. And if we punch that out, which I would expect you to do, 3 to the 9 halves minus 4 divided by 4. You end up getting 34.074. Okay. Same deal for b, just different function. Okay, 5 times log base 5 of 2x plus 1 plus 7 equals 12. Okay, again, I see one log term here, so I'm going to isolate that and get it by itself. I'm going to subtract 7 from both sides. Divide everything by 5. And then when you get to the point where your log term is isolated, to solve you have to use the opposite function, which in this case is exponentials. So we're going to exponentiate both sides, meaning both sides are going to now become power, and the base of that new exponential term has to be a 5. So now those cancel, leaving you with 2x plus 1 equals 5 to the first power. And 5 to the first power is just 5, so when I subtract 1, I get that. And I'm getting x equals 2 as my answer. Okay. And then, I know this is a little bit longer of a video than normal, but we're just going to finish out your note packet together. So for your type 4 problems, these are concentrated on log equations that you have two log terms on the same side of the equal sign, and you have to condense them first before you solve. For example, log base 3 of x plus log base 3 of x plus 1 equals 5. Okay, this is different than your one-to-one properties because they're not on either side of the equal sign. They're on the same side. When they're on the same side, they become a type 4 problem because we have to simplify first using your properties before we solve. So, same base logs, I can combine these into one log by using my product property because of the addition sign. So that's going to condense into log base 3 of x times x plus 1. And you could write that as log base 3 of x squared plus x. Then we're going to do the same thing we did up here when we are trying to get rid of the log to just get to the argument where my x's are. I'm going to exponentiate both sides, giving me x squared plus x equals 3 to the 5th. I'm going to actually punch out what 3 to the 5th is. 243. And then I'm going to subtract it. Because as you can see, we now have a quadratic. And to solve a quadratic, if you can't factor, which this one you can't factor, we're going to use the quadratic formula to solve that. So, quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Simplifying underneath the radical gives me negative 1 plus or minus the square root of 973 all over 2. And so those end up being my two answers. Okay. Just to make you aware, your test over this unit is going to be next Thursday. Your application test, well, actually, we might switch those up where your application test will be Thursday and your test will be on Wednesday, which means you're getting a test review on Monday over all this stuff. And we're obviously going to be practicing it Monday and Tuesday. Yeah. So just expect to test over this stuff Wednesday and Thursday so that you don't have anything to do over break. And that will be it. This is Crisscross signing off.